This is not a natural hill. It's made from rubbish. It's a landfill site. Spread across the UK are more than 20,000 like it, and they're growing. Each year we bury over 12 million tonnes of household waste. Places like this are normally hidden from public view, but they are phenomenal environments, both as an extraordinary archaeological record of our times and full of biological and chemical secrets that could be vital for the future. Of the millions of tonnes of rubbish we send to landfill and bury in the ground every year, what will survive in 100, 1,000 or even 10,000 years? What is modern science doing to change our throwaway society? I'm Dr. George McGavin. In a series of unique excavations, I'm going to dig into 3 very different landfills from the last century to reveal the history of rubbish.
Oh, look at that. Oh, George.
What will it tell archaeologists of the future about how we live today? You can read the text. This should have decayed long ago. My partner in crime is designer and materials scientist, Dr. Zoe Laughlin.
I see landfill as a gold mine. My mission is to discover and demonstrate the incredible value in the materials we waste.
Oh, wow!
Join us on our journey into a secret, unexplored world. With exclusive access to an active modern landfill, we're spending 3 days here carrying out a live study into the extraordinary biology and chemistry of rubbish to ask the ultimate questions. What do we do with our waste today? And could it become a critical resource for the future?
These microbes are having a party in there. This is a living, breathing entity.
What we're about to do has never been attempted on television before. This is the secret life of landfill on an epic scale, carried out on 8 million cubic metres of our rubbish. This landfill is situated on Scotland's east coast. The entire site covers an area of 1 square kilometre. In just 2 decades, the rubbish has been built up to a height of 40 metres. It's a truly mesmerising, otherworldly environment, one that few of us get to see, let alone investigate. It's one of the biggest in the country, the landfill for a major European capital, my hometown, Edinburgh. Chances are, things I've chucked away are over there. One of these dumper trucks holds about half the amount of rubbish each of us produces in a lifetime. This truck holds how much?
It holds between 15 to 20 tonnes.
So that's just one load, but how much does this site take a day?
It takes about 600 to 800 tonnes.
600 to 800 tonnes a day?
Yeah.
That seems an awful lot.
It is a lot. Keeps us busy.
Keeps you busy, I imagine. We're going to go through each stage of what happens to our waste, starting here. This huge shed is where the raw trash first arrives after it's collected from our doorsteps. Despite us recycling nearly 50% of our waste in the UK, as we're about to see, there's tons of potentially reusable materials still being sent to landfill. This site is run by waste management company Viridor, and the guys who work here fight a constant battle to get the trash loaded into their 20-ton dumper trucks and up onto the hill before they're overwhelmed by it. Zoe's already in here and up to her elbows.
Look, take that. Pill packaging, digital watch, little charcoal briquette from a barbecue. It's like...
absolutely horrified.
You don't see this in your lifetime unless you have the opportunity like we are now. You're never confronted with the mass of human waste.
Edinburgh and its surrounds has a population of around 600,000. That many people have sent this much waste to landfill in a couple of hours. In this period, the whole of the UK will have sent 100 times this much to landfill.
I mean, there is everything. Electronics, polythenes, plastics of all types, cardboards, papers, foams, textiles, everywhere you look.
A landslide
That would be
of
a
debris.
terrible death.
That would not be good. That would not be good.
There's a new layer of about 800 tons of rubbish added to this landfill mound every day. With the material makeup of it being so diverse, dense and soft, solid or flexible, organic or synthetic, if it were simply dumped, the hill would take centuries to settle. So how do they make the mound of loose waste stable? This is Billy, and he's been sculpting a hillside out of trash for 20 years. So what's his technique?
The dump trucks bring the waste up here, and then this machine basically compacts all the waste into the ground. So you compact it, you put the waste on like an onion skin. So you're always rolling, always rolling. You take the machine right over the end and come back up and take another thin layer, and that compacts.
What's the force on each of these teeth as it digs into the ground?
4,000 pounds per square foot.
This 55-ton piece of machinery is specifically designed to engineer rubbish, and each fresh load is compressed down onto the contours of the mound. This graphic shows how the landfill looks as a cross-section, with strata of compressed rubbish forming the 40-metre high hill. Buried here is a crazy amount of stuff, 8 million cubic metres of waste.
How did we reach this point where we throw away so much and value so little?
To find out when and how our modern throwaway society began, I'm heading off on our first historic landfill dig. This is the coastal resort of Great Yarmouth.
At the end of the 19th century, Great Yarmouth was a holiday boom town. It was an era when the Victorian working classes first began to enjoy recreational time and have a disposable income. In the summers of the late 1800s, the population of Yarmouth doubled from 50,000 to 100,000. And so did the rubbish.
A kids' play park in Great Yarmouth is the site of our first dig into the secret life of landfill. In the 1890s, this part of the coast was still sand dunes, and this is where the town disposed of all that holiday season trash. They buried it on the beach. You would have no idea it was here today, but I'm joining an excavation led by historian Dr. Tom Licence. He and his team have spent months researching this location, and now they're digging it up.
So, at that time, there were no houses here. This would have been the edge of the town, seas just over there, sand dunes.
Just under the surface, you can see the sand of the original dunes at the bottom, really clean sand.
Victorian Yarmouth dumped 40,000 cartloads of waste in the dunes in 8 years and then turfed it over. It lies just a couple of feet beneath the surface. What will it reveal about our great-grandparents' generation and what they saw as rubbish?
We've got wine bottles, sauce bottles. This is a bottle for Hock, which is like a German wine. We also got some evidence of what they're eating. Domestic food waste, so giant oyster shells and also mussel shells they're eating. And while they're eating these, they're smoking their clay pipes. Cigarette hasn't come along yet.
So that is the sort of Victorian fag end.
Pretty much so, yes.
Yeah.
Once it breaks, you chuck these away. Up until about the 1890s, waste looks much like it did in prehistoric times. You've got ash from domestic fires, you've got bone, and you've got shell, and bits of broken pottery. That's the same all the way through until our period, and it's this period where we see this proliferation of packaging waste. These are bottles for fizzy drinks, like lemonade.
Now that's the one that has a little marble in the top so that it keeps in the fizz.
Yeah, it does.
This is interesting.
Yes. Well, this is an ink bottle. Now, these cost a penny. They'd come with the ink inside already and a cork in the top. You'd use it up, and then when you'd finished, you'd just chuck it away.
So this is the beginnings of the throwaway society. This is when the things are being bought fairly cheaply, mass-produced, and you just then have to chuck them away.
Well, ordinary people have got more money in their pockets. The firms respond by coming up with disposable products, disposable packaging, and it's designed to be thrown away. It invites you to throw it away.
At our Dunbar HQ, we've laid out some of our Victorian finds from Dig 1. What they tell us is that landfill 120 years ago was mostly glass and earthenware, solid materials that aren't going anywhere. Their simplicity contrasts with the far more complex mix of materials we landfill today. So what does that modern mix consist of, and how does it react biologically and chemically when it's all compressed together? Time for Zoe to get hands-on with the hill.
Everything is all mixed up together in landfill, just a mass of stuff. But look closely and you can begin to pick out the individual items. So yeah, we've got aluminium cans, plastic containers, food waste, spring onions, still with their label on. There is something electrical beeping. God, I must find it. Okay. Wow. Smoke alarm. Still got the bloody battery in it. Gosh. These chemicals can leach out, mix with wet food, all this stuff in a giant soup right over there.
As the organic and chemical elements in landfill begin to degrade, seriously toxic fluid builds up and filters down to the bottom. It's called leachate, and it's full of heavy metals and ammonia. So how is this contained? How is it prevented from seeping into the water table and reaching our river systems? To find out, I've met up with Dunbar site manager Barry Folgate at the bottom of what will be a new section or cell of this landfill.
You can see round about us we're stood on some gravel, and before we actually put the gravel in the lining system, we've got a composite engineered lining system, and I've got a bit here before. Before we actually put any waste in, we put a metre of engineered clay down, and on top of that we put this 2mm plastic. And again, it's fully welded. Yeah, that is very strong.
There's no way this is just a hole in the ground.
Certainly not that.
This is very far from being a hole in the ground.
It's certainly not that.
Yeah, yeah. All the fluids that it produces and that leak out will go nowhere near a watercourse.
Nowhere near.
Completely contained and removed off and treated.
It's a fully contained engineered landfill site.
So then you start filling it.
Yep, and we fill it in layers, 3-metre layers normally, and we cover up with soil every night to stop litter from being blown away and prevent pests coming in, birds and things from taking waste away from here.
How long will it take you to fill this area?
We'll have this filled in 2 years.
In 2 years, that'll be an extension to this hill comprising close to 500,000 tonnes of compressed waste. When it matches the contours of neighbouring natural hills, they'll cap it off with a plastic membrane, a couple of metres of clay, then soil and grass. This process completely seals up the waste. The bacteria in the rubbish use up all the oxygen, and the atmosphere inside the mound becomes airless. But our waste has only been managed with this amount of care for the last 20 years. We've been throwing away things and burying rubbish on this scale for much, much longer than that, and with far fewer safeguards in place. To get more insight into the history of rubbish and how we've got to where we are today, we're going back in time 60 years for landfill dig number 2.
Before World War II, almost all of the rubbish we produced was burned. And then in 1956, the government introduced the Clean Air Act. And that really was a turning point. It meant instead of burning all our waste, we buried it underground on a massive scale.
The 1950s was also the era when the government told us that we'd never had it so good. Gone was the austerity of World War II rationing, in came consumerism, and with it a whole new range of synthetic materials and disposable products. London got rid of its rubbish by shipping it down the Thames on barges and dumping it on the estuary's marshlands. At first glance, you wouldn't know that this was a dump site today. It dates back to a time before we lined and sealed up landfills. But look a bit more closely and you'll see that some of that 70-year-old rubbish is re-emerging.
You can see what's happened. Coastal erosion has just eaten this all away. And now all this rubbish, and there's a lot of it, is just being washed out onto the beach and out to sea. And it's bloody horrendous. I've never seen such a mess in my whole life.
I've arranged to meet environmental geochemist Professor Kate Spencer, who along with technician Sean Kennaway is currently investigating the threat that coastal erosion poses to our landfill legacy and ultimately us.
There's no records of what went in here. We just know that it's a mixture of commercial, household and industrial, all kind of mixed together. And when we analyse it, we're really analysing the contaminant levels of all of that mixed up.
All mixed up.
Yeah.
I've been told that if I'm to handle anything, I have to wear gloves and on no account put my hands near my mouth, nose or eyes.
Plastics, of course, are coming in now. Here's egg containers, like a big stack of egg boxes. And it is breaking down, but into tiny, smaller pieces of plastic.
I mean, it's pretty clear that all of that is going to end up as a microplastic broken down in the Thames. And actually, look, you can see here a whole layer of fabrics. And these must be synthetic. I mean, they've maintained their colour and integrity over decades. And actually, a lot of people think about the problem of microplastics being broken up plastic bottles, but it's things like these nylon fibres and polyester fibres. They get broken down and eroded and released as well.
So these microplastics will get digested by the plankton-sized marine life. They in turn get eaten by fish, and that plastic goes up the food chain and finds its way into our diet.
That looks like a piece of asbestos.
In fact, look, all of
Sheeting.
this
Yeah,
is
all of it.
asbestos sheeting.
That's nasty, nasty stuff.
Asbestos is a naturally occurring mineral and was used in construction for decades in the last century, but its crystalline fibres can cause lung cancer when inhaled.
And that's all breaking down into small bits and drifting around or ending up in the ocean.
Yeah, in fact, I'd rather not handle it.
Okay. So what's this big lump here, Kate?
Okay,
Yeah.
so I think this is a battery pack of some sort. So you can see
God, yeah.
that all the outer casing is all kind of corroded.
So it's a big lump and they're all joined up.
There are hundreds of batteries like this on the beach, and they can contain cadmium, a carcinogenic heavy metal. Sean has a bit of kit that can analyse the battery cluster at a molecular level and read how high the trace elements of cadmium are and what other toxic chemicals it might contain.
So what actually is this machine he's got? It looks very neat.
It's a portable X-ray fluorescence analyzer. So it emits X-rays, which is why we're standing back. And the X-rays have energy. And when that energy interacts with the material that Sean is analysing, it excites the atoms. They release energy, and that energy is indicative
Of what the atom is?
Yeah, of what
so
we're looking at.
you can tell if that's got cadmium or arsenic or
Yeah,
carbon or zinc, whatever.
yeah,
I know what I'm going to ask for this year
for Christmas.
for Christmas. Yeah, I'm going to get.
Now this will take about, it's like 3 minutes run time.
Okay, so that's now analysed.
Yep.
What are the results, Sean?
Yep, so we've got arsenic at 132 parts per million. We've got cadmium at 135 parts per million. lead at 1,920 parts per million, and zinc at over 280,000 parts per million.
Kate, that sounds pretty bad.
If you compare those kind of values with environmental guidelines, cadmium for an environment like this is just 1 or 2 parts per million. Zinc is perhaps a few hundred. So these are several magnitudes higher than those environmental guidelines.
And as that breaks down further, all those elements will end up in the silt, in the sediment.
Yeah, and when the tide comes in, all that material will be carried out into the river.
What's worrying me particularly about this is that we know we're having chance events. Storms are coming, they'll be more frequent, perhaps severe.
This is what we're concerned about. With climate change, we know that storm frequency is increasing, coastal storm frequency is increasing, then that could release a large volume of material.
Well, this is an incredible place, fascinating but depressing. What we're seeing here, exposed like this, is garbage that was thrown out 60 years ago by householders who then thought their material would be taken away, disposed of. Well, it's still here. And it's coming back to haunt us. And you do have to ask yourself what's going to happen with the large volumes of garbage and materials that we dispose of today. What effect will that have on our well-being in the next few decades of the 21st century and beyond?
It's the second day of our live study into landfill. Now we're going to explore the bigger picture and the side effects that burying our rubbish has today and will do in the future. A major concern today is synthetic plastic breaking down into microparticles and contaminating our environment. So can science develop an alternative to plastic that considers what will happen if it ends up in the wider world?
Well, this is the ubiquitous plastic bag. These days we get charged 5p for them at the shops, and globally up to 1 trillion bags are used every year. They get everywhere, even into our oceans, where they are literally choking marine life. But take this, good strong plastic bag. Watch what happens when I put it into some lukewarm water.
Because this is made from a plant-based material, the bonds binding it together at a molecular level are much weaker than those in a bag made from oil-based plastic.
It's made from starch from a plant called cassava, and it dissolves very easily in warm water.
Leave it out in the open air, and in a matter of days it breaks down into non-toxic liquid and carbon dioxide. Warm water simply accelerates the process.
And it dissolves so well that in a couple of minutes it's virtually disappeared. And now this is the plastic bag that's really safe for all forms of wildlife, including me.
With innovations like this, science is proving that it can transform the impact our throwaway society has on the planet. But there's a lot more to managing our waste than just solving the plastic problem. Even when rubbish is buried in an engineered cell and sealed up, it still produces an extremely hazardous side effect, methane gas. So what's causing it, and why is it so dangerous?
In this landfill site, as was shown in the pie chart earlier, we actually have a surprising amount of organic material. And bacteria are acting on it, breaking it down and actually producing gas, and specifically methane, that's really, really dangerous, highly flammable. I can't see it or smell it, and that makes methane risky to be around. And in fact, I have to carry this methane detector with me, because if the levels get to a certain point, this will sound an alarm and we have to evacuate. Methane is 1 part carbon, 4 parts hydrogen, and it's so combustible that a naked flame is strictly forbidden on the landfill. So to demonstrate what could happen if even a few sparks ignited up here, I'm heading down to the beach near our site. And what I'm going to do is absolutely not something you should try at home. This is a canister of compressed methane, and I'm now going to turn it on, and I'm now bubbling it through this washing up bowl of water with lots of washing up liquid in, generating loads of suds. And those suds, each bubble is a little pocket of methane gas. Right, that's probably enough. Now to prove how flammable this is, I can scoop some up. Whoa, the wind, hang on. Right, hold on. And with the blowtorch, oh, wow! Wow, okay, that perfectly demonstrates the problem that landfills face. Methane is incredibly flammable. Wow, that was great. Let's do another one.
But what on a landfill site could cause methane gas to ignite?
Well, it could be something as mundane as this. Landfill fires started by lithium batteries are a very real danger for sites like this, especially when machines as big as that drive over things as invisible as this. The inside of the battery is exposed to oxygen and produces small sparks. Combine that with a pocket of methane, kaboom!
There's constant risk of a methane explosion or fire on a landfill site like this. But incredibly, this hazard is exploited as a resource. This isn't just a massive rubbish dump, it's a giant gas platform. The site is studded with dozens of wellheads. They actually mine the methane to power gas turbines that generate electricity. And here at Dunbar, this operation is overseen by energy recovery engineer Michelle Moran.
So on this particular site, we have 300 different wells. We have 18 kilometres of pipe.
How many houses could that heat, say, for a day's output?
Enough electricity for 8,000 houses.
And that's great. I mean, it's very interesting that we're standing here in a site where I can see 3 different kinds of energy production. We have a reactor over there, we have wind farms over here, and we've got the production of landfill gas here. How much, if you were to compare the output per hour of the landfill site with, say, a wind farm?
Each of those turbines there produce 1 meg normally if the conditions are right, whereas we will sustainably produce 4.5 megs all day long, 24/7 from this site.
Effectively, Edinburgh's waste and the surrounding areas are producing the same power off this landfill gas that would be produced by 4 or 5 wind turbines.
Absolutely, but the most exciting part about this actually is it's the microbes within this landfill site. This is a living, breathing entity. Now remember, the gas is being produced 24/7 as these microbes are living in this fantastic environment. They're having a party in there, producing all of that gas, and we have to deal with it. Remember, they're feeding off the waste.
It's just the organic, biodegradable waste that the microbes feed off to make methane. But some scientists argue that if we can further develop this process, then methane could be the fuel that gets us to Mars and beyond. So if we could see our organic waste as an energy source, would we stop sending it to landfill? Is there a way for us to give even the worst of waste a value?
Well, I've come down to the beach beside our site, and it's popular with dog walkers. Now, this is the ubiquitous dog poo bag, which all responsible dog owners should be familiar with. Hundreds, perhaps thousands of tons of dog poo end up in landfill every year. Now this stuff is really going to produce methane when it's sealed up in a landfill cell.
We've been joined at Dunbar by engineer and inventor Brian Harper, who has perfected a way of transforming dog poo into methane gas to power a street light.
This looks like an amazing contraption. What does it do?
It takes dog poo, which we encourage people to pick up because they have a very simple way of doing it with this bag. And it biodigests the dog poo down and generates biogas.
Which is essentially methane.
Mostly methane, a little bit of carbon dioxide, but that's not a problem.
And how does it work? You just heave the poo in the top?
Yes, it has to be seeded first of all with the bacteria, the methanogens, which then will eat away at the dog poo and anything else that's biodigestible.
Right.
And from there we then generate the gas, which comes and bubbles out, and that is then caught into a gas holder, which is what we have at the front.
This is just a prototype, but what Brian's utilising is an anaerobic digester in conjunction with bacteria, methanogens, to generate the gas. It's capable of producing fuel from any organic waste, including food. So imagine a more refined version of this biofuel technology in every household.
So it all goes in here?
Yes, that's it.
And then you turn the handle to aerate it?
Well, all that does is push the bag into the biodigestate.
Pushes it in, right, into this bit here.
Yeah, and the dog owner walks away, the kit then looks after itself, and it gurgles away, and from around about 10 bags per day.
10 small poo bags?
Labrador bags. That will generate enough gas to run a gas lamp for about 1 to 2 hours. It's all that's needed.
It's absolutely a win-win. I mean, every village, every town on a street corner should have one of these.
Yes.
If you could just train the dogs to shit in the machine themselves, that would be even better.
Even better, yes.
But if bacteria is only breaking down and producing methane from the food waste in landfill, what's happening to the rest of it? The buried plastics, the clothing, the metals. Is that breaking down at all? Does it eventually rot away to nothing? And if so, how long does it take? I'm constructing a garbology graph to give us a notional sense of how long it takes some of landfill's most common items to degrade. According to numerous studies, food waste should break down pretty quickly. Banana peel in 2 weeks to a month, paper in a month or two, and natural fibres like cotton or wool between 6 months and a year. That's because the bonds holding some materials together at the molecular level are delicate and break apart easily. But the moment we get into synthetic material, so anything with plastics in it, you have molecules that are bonded together by more robust chemistry. And we see a massive leap in degradation times. So instantly we're jumping from months to decades. So it's 30 to 40 years for nylons, polyesters, synthetic fabrics. The degradation of aluminium cans has been estimated at anything between 50 to 500 years. Wow. And the same goes for babies' nappies. So if Elizabeth I wore a nappy and drank from a can, they would still be around today. And plastics, some bags will break down, but what will happen to those buried in landfill? Glass, well, that'll be around for thousands of years. And it's suggested that more complex, denser plastics will never break down. But it's all dependent on environmental conditions. These degradation times only apply to materials being left out in the open, exposed to moisture and oxygen and the UV and sunlight.
The fact is, nobody really knows exactly what's happening to the matrix of materials that we bury in landfill. Because we entomb our trash in an airless environment, it could be lasting a lot longer than we expect.
So what will archaeologists of the future discover when they dig into our landfills? And what will it tell them about how we live today? To put Zoe's materials degradation graph to the test and find out how long the things we throw away actually last when we bury them, we're setting out on landfill dig number 3. And this time, we brought along a 13-ton digger. This landfill site is on the outskirts of Birmingham, and between 1982 and 1988, it was filled with 1 million tons of household rubbish.
And we're going to dig it up to see what's happened to the material that was thrown away 30 years ago. Has it degraded, or has the compressed, sealed up world below our feet actually preserved our garbage?
This 30-year-old landfill dates from an era when some thought went into burying waste. It used to be a quarry, so the rubbish is at least contained. And when it was full, a layer of clay was laid over the top to seal it up. That means what's in there will have been deprived of oxygen for 3 decades.
How deep will this hole be? This is going to be 5
meters
more. Yeah.
I know, I actually can't quite believe what's about to happen here. A mass of stuff that was put in the ground when I was born is about to emerge. Stuff which hasn't seen the light of day for over 30 years.
Oh, a bit of garbage there.
Our first bit of rubbish.
Right. We are ready to receive 80s garbage.
Bring it on. Clothes, loads of textiles.
It's funny, this has a sort of slightly sweet, acidic smell to it.
It's slightly bin juicy, but not even as bad as your own bin could
because
be.
What you have in your own bin, of course, has access to oxygen.
Yeah.
Whereas this hasn't had for a very long time.
George, baby's dummy.
And the person who sucked on that will now be...
My age.
Yeah.
Look at that, and that's 2 different types of plastic. Do you know what? Nowadays this would have a recycling mark on the bottom, this one doesn't.
No.
A pair of trousers.
A pair of trousers.
Can we see on the care
Trousers.
label what they're made from? Polyester and cotton. So yeah, poly-cotton mix. That's not degraded one bit. This stuff just lasts, doesn't it?
Oh, so we sure are. It's a little dress. Look at that. Isn't that sweet? That's completely... Look, it isn't even decayed. Look.
This is an extraordinary find. Synthetic clothing that's been buried for 30 years but still looks pretty much brand new, where my estimates suggested it should have at least started to break down. And in this 1980s era rubbish, we're also finding product packaging that could still contain chemicals or gases.
Hey, wait a minute. Harmony hairspray. That was all the rage, wasn't it?
Yeah. George, this is a nappy and it's got a kind of solidity inside. That is a poo, if ever I felt one.
Are you sure? It's just a wet one. Look at that. Recognisable as a child's nappy after 30 plus years. And still, you know, retains a certain degree of strength.
But disposable nappies will hang around for hundreds of years. This is still brand new, essentially, in the life of this nappy.
But then we make a shock discovery, something that really should have degraded decades ago.
Newspaper, still legible. Look at that.
Let's see if we can find the date.
It can be
it's
read.
The bottom.
Cricket Club threat.
Oh,
I find
there
this
you go.
incredible that you can actually open a newspaper that was buried 30 years ago in a landfill and you can read the text. This should have decayed long ago.
Yeah,
but
this should go in weeks.
Yeah, but because it's in a completely airless environment, it's actually been preserved.
Look at that, 1986.
86, and you can still read. Look at the hairstyles on that. Will you look at that? What was on TV? We've got Match of the Day. We've got Sue Pollard and Heidi High at 7:15. House prices. Oh, God.
Yeah, my God.
How much is the house price? Quick.
We've got 3-bedroom house.
For
£30,000.
This is going to be an archaeologist's dream in 1,000 years' time, if it's still there, which it probably will be. And what it brings home to me is that it doesn't just, out of sight is out of mind, but it's not, it's still here in the environment. And you might just put it outside your house on a Tuesday afternoon for it to be taken away, but it doesn't go away. Once it's made, it stays around.
And it's not just the rubbish that remains. 30 years after this dump site was closed, it's not only still producing methane gas. Leachate, the liquid element of rotting waste that's full of heavy metals and ammonia, continues to seep out the bottom of it.
You know, what really stands out for me is that I, like everybody else, have been sending bags of rubbish to landfill for decades, and I haven't really given it a second thought. It's really shocking that the stuff I threw out years ago is still pretty much intact, and it's contributing to a vast land contamination problem that could last for centuries.
It's day 3 at our Dunbar landfill HQ. Now we want to focus on how we might fix the landfill problem. How do we ensure that our children's children don't have to manage the things we throw away for decades or even centuries simply to avoid environmental catastrophe? The straightforward answer is dig our landfills up, and why not? They're full of valuable materials that we can recycle, materials that the planet only has finite amounts of. Plastic is made from oil, and we know we're running out of that. And metals. Current estimates suggest that many known sources of metal ores on Earth will run dry in the next century. So why not mine landfills for these valuable resources?
I'm going to carry out my own mining operation to demonstrate the unseen but quite phenomenal value in one of the most common items we discard today, the smartphone. Right, an icon of our age, really. To me, mining landfill for metals makes sense. Sources of metal are limited, particularly those classed as rare earth elements. And my research tells me that the average smartphone is packed with them. It contains around 75 different elements. It's a periodic table on its own, really. So I'm going to perform a unique autopsy to see how many I can find and reveal how precious the things we throw away can be when we look at them more closely. But just the screen alone is an incredible feat of engineering and material science. Okay, we're in. Right. Ooh. Here is a bundle of extraordinary layers of incredible elements that give colour to the image. I can just prise these off. But each one of these is microscopically layered with elements like terbium, yttrium, gadolinium. Pretty exotic elements, really. Stuff that we go to huge efforts as a species to mine and process. It really feels like a kind of dissection of a modern icon. You don't think about the stuff that lies behind the experience of your phone. Right, so now we need to break in further. In fact, well, let's get the SIM card out. So there's our first bit of gold. We're into the back. Yeah, these things aren't designed to be opened. Ultimately, that doesn't make the materials in here very recoverable. They are incredibly valuable and useful. Okay. Okay, so we're in from the back. So here's our lithium-ion battery. Basically, any rechargeable consumer electronics will have batteries like this. Lithium cobalt on the cathode, so that's the positive part, and carbon on the anode, that's the negative part. What, that is so small. Beautiful precision screw. But imagine trying to take this thing apart in order to retrieve the materials, the time and labour that's going to be involved in unscrewing all these screws. Look at this. So here is our camera unit. So there's gold on all of these connectors. There's gold on them there connectors. There are now more mobile phones on the planet than there are people, and their average lifespan is around 2 years. If you're anything like me, you know, all my old phones are in a drawer at home, but you can totally understand people thinking, oh, have a clear out, what do? Throw them in the bin. And that means they will end up in landfill sites. And it's estimated that there are millions of these things going to landfill sites every year. Right, here we go. There's the CPU, that's the processing unit, that's the brains of the operation. So that's silicon, there's arsenic in there, antimony, gallium, phosphorus, all sorts of incredible materials go into making these chips. Now look, here's larger bits of gold in here. These connectors, all gold, really valuable stuff. It's been estimated that some of the rare earth metals that are so essential to our device-driven existence will run out in the next 20 years. There have been 12 wars fought over these resources in the Congo in the last decade alone. None of these elements are easy to obtain. Mining methods are hugely inefficient. It takes a ton of gold ore to just make a single gram of gold. But I could retrieve a gram of gold from just 40 smartphones. These are very, very valuable. Not just because it's gold and we understand that that has a monetary value, but because there's elements in here that there's just a limited amount of, and we need them to do these high performance functions. For me, metal is one of the greatest treasures in landfill and absolutely makes them potential gold mines.
And along with metal, there's another material in landfill critical to our modern existence: plastic. We know that we can recover plastic from landfill, but what's the best way to get rid of it? Now, an exciting new discovery could see us on the verge of a recycling revolution. At a waste site in Japan, scientists discovered a newly evolved bacterium that was actually eating plastic. What I find extraordinary about these cells of landfill garbage is that once they're filled up and sealed, the bacteria inside quickly use up all the oxygen, but there's still things alive in there. I've got a sample of the leachate, the fluid that seeps out of the bottom of the cells and is collected. And inside here are anaerobes, specialist bacteria that basically evolved to suit this environment, and they're surviving on our waste. I've recruited bacteria scientist Dr. Claire Taylor to help perform a unique analysis of microorganisms in leachate. Hey Claire, I bring you a sample of leachate. It says best before, no it doesn't. That's it. What next?
Great, thanks George.
Can we have a smell of it?
Well, okay, you can go first though.
All right. I mean, it's hard to believe anything survives in this. Ammonia, sort of this cheesy feet, no?
Oh yeah, lots of ammonia
Cheesy
in there.
feet? Yeah, that's not pleasant. Now, what do you think's in here?
This will be absolutely teeming with microbial life.
That survive without any oxygen at all?
So we can take a sample out and we can have a look. So I'm just going to pop a bit on the slide.
I'd have got you a smaller bottle if I know.
So George, if you take a look underneath the microscope, what you should be able to see is a stain sample of bacteria. You can see them on the computer screen here from the camera.
Now, I mean, I'm seeing a lot of just a big blue smear, but this is blue because you've stained all the bacteria.
Yeah.
And there are literally trillions of them. I mean, each tiny dot there is a bacterium.
Yeah, absolutely.
And this is a tiny fraction of the whole drop.
Yeah.
Which came out of this bottle here.
Yeah. So it's really, really dense in some parts of the slide.
This is absolutely extraordinary.
I mean, the key point here is that there are literally, on the screen we're looking at, you know, tens of thousands, hundreds of thousands of individual bacteria.
That is quite extraordinary. And they're surviving in this hellish, airless environment.
Yep.
Now that tells us that there are lots of them in this.
Yep.
What's the next step?
In order to find out what they actually are, what I'm going to do is extract the DNA from the sample and sequence it. I'm going to use this amazing device, which will...
That
Yep.
is a sequencer.
It is.
That is a DNA sequencer.
It is. It's a portable DNA sequencer. It's designed for use in places like this. So we literally open it up and we put a little tiny spot of the DNA that we've extracted into the device, and it runs through and it sequences it in real time.
So once we've extracted the DNA from these bacteria, you can compare that to known sequences of other bacteria, which will hopefully inform us about what we've got here.
As far as I know, nobody has actually done this before.
Claire, good luck.
Okay,
I'm
thanks.
going to leave you to it.
Awesome.
I can't believe it. DNA sequencing in a landfill.
What we hope to find is unclassified DNA. If there really is new life that's evolved to break down rubbish, particularly plastic, then the more we understand it, the closer we get to having a range of biotech tools to repurpose our waste. Time to find out if our bacterial DNA test has turned up any interesting results.
Well, hi, Claire. This must be about the most difficult working environment you've ever had, surely.
I have to say, it's been quite challenging.
Yeah. But have you got something?
Well, George, from the sample that I put through this sequencer here, I have indeed got some data back.
Right. Tell me the bottom line.
Okay, so I can show you here.
This is very exciting.
So, 87% of our sample is bacteria. 12% of our sample is eukaryotes.
That's higher organisms,
yeah,
like
so yeasts,
single-celled organisms like
humans.
Yeah, bits and pieces.
And then we've got a really small proportion, less than 1% of archaea.
That's these really ancient bacteria.
Yeah.
So it's a really interesting mix.
It is indeed. Now, interestingly, so we've analysed 3,841 reads.
So that's a very rich drop of fluid.
Absolutely. Okay. So of those 3,841, 700 of these have been classified. And
right.
3,141 of them are unclassified. That means we don't know what they are.
Okay, so these are bits of DNA. 700 of the bits of DNA are known. They belong to organisms that we have a name for.
Yes.
But there are 3,141 bits of DNA which cannot be fitted to any known bacterium or organism.
Yeah, that's right, based on the information that we have. Okay?
That's incredible. Now, which means, well, to me, and correct me if I'm wrong, that suggests very strongly that there are undescribed species of bacteria in this sample, in that one drop.
That is very, very possible.
This is unclassified new life that has evolved in the unique airless environment of landfill. And it might just be possible that some of it is breaking down the plastic elements in our waste.
This fluid is incredibly rich. It's absolutely stuffed full of things.
Yep.
Things that we don't know anything about, things that could hold the key for future advances in how to deal with this stuff.
Yep, that's absolutely right.
It could be that in this bottle there are microorganisms that have evolved to break apart plastic. As this kind of research continues, there's every chance science could be on the verge of a breakthrough, a way of perfecting biotech that ensures that all plastics can one day be efficiently recycled and reused. On our epic journey through the past, present and future of rubbish, we've made some fascinating discoveries. Not least that in just over a century, an incredibly short period in the rise of a civilization, the complexity of our waste has evolved at a mind-boggling rate.
This is an extraordinary timeline of trash from the 1890s, 1960s, 70s, 80s, all the way into the 21st century. We've got these extraordinary array of materials, but what strikes me is many of them have been designed really to be used for a very, very short period of time, even once. From the kind of ink bottle of the Victorian times, this was the disposable biro of its day, to single-use cosmetic products from the 80s, babies' nappies, single use, you wouldn't want to reuse that. All the way to the plastic bottles of today. This stuff is designed to be thrown away, and it's such a shame.
Perhaps we should think about hanging on to things for longer and not just going...
Yeah, but making them so that they're designed to be disassembled and recycled, or made to be treasured, or there's all sorts of different approaches. But how we make things also affects how we unmake things.
All this stuff, ephemera, one use. And what are archaeologists going to think? You know, because all this stuff will survive us and probably survive in the ground for 1,000 years. What will archaeologists think when they dig this up?
They're going to think we're bonkers. I mean, they're going to think we're a civilization with great capabilities, but at the same time, we had no idea what we were doing.
Ultimately, we've revealed that the story of our rubbish is also the story of our civilization. As we keep upgrading our lives, we keep throwing things away at such a rate that we're only now catching up with ourselves and learning how to value and repurpose the limited materials we have.
In this investigation into the secrets and science of landfill, we've discovered that what we throw away today will need to be managed for generations to prevent it from becoming a toxic time bomb. We know that there are materials buried here that will outlast us for hundreds, perhaps even thousands of years, and that material could one day become an essential resource.